Okay, so we've defined metric spaces, and now we're going to talk about a vector space. Before we talk about vector spaces, we need to talk about this notion of a field. Okay, so a field is a set of scalars with well-defined addition and multiplication operations. So examples of a field might be simply real numbers with normal addition and multiplication. Might be complex numbers with complex addition and complex multiplication. Could be a set of quaternions with addition and multiplication. Or maybe a set of binary numbers where the addition is the OR operator and multiplication is the AND operator. All right, so given a field, a vector space is going to be this pair. It's going to be a set X and a field F, where X is just a set of objects and F is a field. And X has to be closed under addition and scalar multiplication. In other words, if little x is in our set X and alpha is in the field, then alpha X has to be in X. And little xy is in capital X, then X plus Y has to be in X. So by implication, if we have, for example, X and X, then alpha beta in the field, then we can add elements of the field and we're still in X. We can, scalar multiply the addition, we're going to be in X. Or we can scalar multiply both X and Y and we're still going to be in X. So think of a vector space, if we have some X, then we can multiply, anything along here and we're still going to be inside of X. So if X is in R2, and then we could, alpha X might be out here. Or if Y is like that, then, X, this would be X plus Y. It's still going to be in R2. And so R2 turns out to be a vector space. Okay, so one thing to note is that this the field always has a zero element. And so, multiplying by 0 means that the 0 element has to, X has to have this has to have a 0. And so, a vector space has to contain the 0 element. So we can talk about subspaces of vector spaces. So we have V is a subset of X. We say it's a subspace if V is also a linear vector space. In particular, it has to contain 0. So in other words, here we have R2, and then V is equal to the span of, alpha 1, 1. Then, this is a vector space. Because anything here, if we scale it, it's going to still be in that space. If we add vectors that are in V, then we're still going to get vectors in V. But here, if we have some X and then we scale it, we immediately go off. Or if we say X plus Y, that's going to give us a Z out here, and that is not in V, where this is V. So this is not a linear vector space. So examples of vector spaces, the set of Rn and then the field R. Now if you had the set or this complex numbers with the field complex. Now if you had real numbers with the complex field, would that be a vector space? No, because when you multiply you get complex vectors and they wouldn't be in Rn. But if we were to have complex Cn with a real field, that would be valid. We can look at real matrices and the field would be real. That would be a vector space. Or the set of continuous functions with a real field would be a vector space, or the set of bounded sequences with real field, or the set of bounded functions with real field. These are all valid vector spaces. But things that aren't a vector space, so for example, if you take the Cartesian products of the reals with 0 to 2 pi, so you have a real number and then you've got 0 to 2 pi. This is a cylinder, okay? This thing is not a vector space. Again, you take an element out here, and if you scale it, you immediately go off of the cylinder. And this is the state space for an inverted pendulum, where you got the angle and the velocity. So you have a lot of interesting, spaces that are not vector spaces. Also, the set of rotation matrices with any field F. So, for example, R1 being a rotation matrix plus R2, this is not a rotation matrix. And any scalar R, this is also not a rotation matrix. Rotation matrices are very important in robotics and other applications. Set of unit quaternions is not a vector space. Quaternions are used extensively in robotics and quantum mechanics and computer graphics. So there's a lot of useful elements, or a lot of useful sets that are not vector spaces. Okay, one of the most important concepts with a vector space is this notion of linear independence. So, what is that? Let S be a vector space, and now let T be a subset of S. Okay, that's what this means. It's a subset. It's part of S, but not all of it. So a T is a subset of S, and T may be, some countable, or even infinitely, or maybe even uncountable set. So T is linearly independent if for each finite non-empty subset of T, in other words, P1 up to Pn, this would be finite because the n is not infinity, some finite subset of T, where Pi is in T, we have that the linear combination of those vectors is equal to 0 if and only if the coefficients are equal to 0. Obviously, if the coefficients are equal to 0, this whole thing becomes 0. And so, this guy equal to 0 has to imply that the coefficients are equal to 0. Otherwise, this set T is linearly dependent. All right, so let's do some examples. So for example, if S, the vector space, is R3, then this set 1, 0, 0, the vectors 0, 1, 0, are linearly independent, because if we take a finite, linear combination, C1 times the first one plus C times the second, that's going to be equal to C1, C2, 0. And the only way that can be 0 is if C1 and C2 are 0. And, but, another example, if you let the set be 1, 1, 0, 2, 2, 0, this is linearly dependent, because if I take a finite combination, I'll get both of these elements give me C1 plus 2C2, and this can be equal to 0 if, for example, C1 is minus 2 and C2 is 1. As only one example. There's many different combinations of C1 and C2 that give you 0. So this set here is going to be linearly dependent, where this set up here is linearly independent. Okay, so we also have this notion of span. So let S be a vector space, and let T be a subset of S. Okay, then this set, the span of T, is the set of all linear combinations of T. In other words, you sum all these together or scale them with the field, sum those together, that's going to be everything in the span of T. So for example, if I have this vector 1, 1, the span is going to be all linear combinations. So I can't add anything because there's just one, but I can scale it by any element in the field. So that would be the set of alpha, alpha, where alpha is in the real. So this means this is the set of all vectors that look like this, alpha, alpha, where alpha is a real number. So it's going to be this line, because this is 1, 1, and then I scale it by alpha, I get everything in this line. So that's the span of 1, 1. The span of 1, 0, 0, 1, this will be, anything of the form alpha 1, 0 plus beta 0, 1. So that's alpha, beta. So it's going to be anything of the form alpha, beta, where alpha and beta are reals, which means it's all of R2. Okay, so the span of this set 1, 0, 0, 1 is going to be all of R2. Okay, and that leads us to this very important idea of a basis. Okay, so we say that T is a basis for the vector set S, vector space S, if two things: T is linearly independent, and the span of T is equal to S. Okay, and then we can define also the definition. In other words, we have T has to be linearly independent. We can't have vectors that are dependent together, so you have to be linearly independent. And then if you take all linear combinations of those things, you have to get S. So all linear combinations of T, you have to be able to get to S from some linear combination of T. And there really is only one way to do it, right? Because they're linearly independent. So the dimensions of the vector space S, now we're going to talk about the dimension, is the smallest number of linearly independent vectors needed to span S. So, for example, the vectors 1, 0, I don't know if I probably don't have a good example. These are linearly dependent. But we could have 1, 0, 1, 1. Yeah, these are linearly independent, and they're linearly independent, and they span all of R2. These span all of R2, but they're not linearly independent. So we have to have it's the smallest number of linearly independent vectors needed to span the space. So as an example, a possible basis for Rn would just be, these vectors where you have 1 in the ith column and you have n of them. And so there's n of those, so the dimension of Rn is going to be equal to n. If we have the set of bounded functions, then, one basis would be, again, 1 in the first element, 1 in the second, all the way up to 1 in the nth, all the way, and going on for infinity. And since these are infinite sequences, and we have, infinite number of linearly independent vectors needed to span the space, the dimension of L infinity is in fact infinity. You could think about the set of all polynomials P. So a basis for the set of polynomials is going to be 1, t squared, t cubed, t the fourth, etc. And there's an infinite number of those. So the dimension of the set of all polynomials is infinite. Or you could think about the set of all polynomials of degree less than or equal to q. We'll call that pq. So a basis there would be 1, t squared, up to tq. We don't need anything more because we don't need higher degrees. So in this case, the dimensions would be q. These should be set.